Prime numbers are the atoms of arithmetic, the indivisible elements from which all other numbers are constructed. They are simple in definition, numbers greater than 1 that are divisible only by themselves and 1. Yet their behavior is anything but simple. These primes are the building blocks of all whole numbers, forming the foundation of mathematics, much like atoms form the foundation of matter. Every whole number can be uniquely broken down into a product of primes, a fact that underpins much of number theory. Their distribution has fascinated mathematicians for centuries, appearing random, yet hinting at a hidden order. Despite their apparent unpredictability, patterns seem to emerge, sparking curiosity and inspiring generations of thinkers to search for deeper meaning. This enduring mystery led to the Riemann Hypothesis, proposed in 1859 by the brilliant mathematician Bernhard Riemann. He suggested a profound link between the distribution of prime numbers and the properties of a complex function known as the Riemann zeta function. Riemann noticed that certain points, called non-trivial zeros, all seem to fall on a single straight line, the critical line. This observation hinted at a hidden symmetry, a kind of mathematical harmony underlying the apparent chaos of the primes. The hypothesis claims every one of these zeros lies on this line, but no one has ever proven it. The challenge is immense, requiring tools from analysis, algebra, and even physics, and has resisted all attempts at a solution for over 160 years. Trillions of zeros have been checked, all matching Riemann's prediction, but mathematics demands a proof, not just examples. Computers have verified the hypothesis for unimaginable numbers of zeros, yet a general proof remains elusive. Solving this would unlock secrets about numbers and revolutionize fields like cryptography, which relies on the unpredictability of primes for secure communication. The implications would ripple through technology, science, and our understanding of information itself. The Riemann hypothesis is more than a puzzle. It's a gateway to understanding the universe's mathematical fabric. It connects the abstract world of numbers to the very structure of reality, hinting that mathematics is woven into the cosmos itself. Its solution remains one of the greatest quests in mathematics, a challenge that has inspired countless minds and continues to drive research at the frontiers of human knowledge. The search continues as we try to decode the hidden music of the primes, a symphony that, once understood, could reveal new truths about the universe and our place within it. For over 150 years, mathematicians have attacked the Riemann hypothesis with analytic number theory, complex equations, and abstract structures. But what if the answer lies not in analysis, but in geometry? Researcher Robert Edward Grant proposes a radical shift. The critical line isn't a coincidence, but a geometric necessity. He suggests the prime's distribution is governed by dimensional rules, much like a shadow's shape is determined by its source. This approach seeks to explain not just where the zeros are, but why they must be there. If true, it could transform our understanding of primes from abstract chaos to elegant geometry. Numbers, in this view, might reflect the rules of space and symmetry itself. At the heart of Grant's argument is a simple geometric truth. Boundaries are always one dimension lower than the space they enclose. A cube's boundary is its two-dimensional faces. A sheet's boundary is its one-dimensional edge. Grant applies this to the Riemann zeta function, defined over the two-dimensional complex plane. He argues the prime number fluctuations are a phenomenon within this plane, and their boundary, the non-trivial zeros, must be one-dimensional, a line. This, he claims, is the critical line. The zeros aren't mysteriously aligned, they're constrained by geometry. The critical line is a necessary boundary, not an accident. This reframes the question. Not, Why are the zeros on the line? But where else could they be? The answer, Grant suggests, is dictated by the fundamental rules of dimensionality. The critical line becomes a geometric inevitability. If primes are shaped by geometry, what's the structure? Grant points to the cuboctahedron, a highly symmetrical Archimedean solid. This shape, called the vector equilibrium by Buckminster-Fuller, represents perfect balance, all forces in harmony. Grant proposes this equilibrium is the geometric engine behind the primes distribution. The cuboctahedron's unique symmetry and balance provide the framework for how primes unfold along the number line. Imagine the number line as a projection of this perfect form. The cuboctahedron's properties dictate the rules for the prime's appearance. Numbers, and especially primes, emerge from perturbations of this balanced state. Like ripples from a pebble in a still pond, primes are the echoes of a geometric disturbance. The shape itself encodes the laws that govern the prime's mysterious rhythm. The cuboctahedron's 14 faces are more than static geometry. They're active in Grant's theory. 8 triangular faces represent creation, generating candidates for primes. 6 square faces act as constraints, filtering and shaping which numbers become primes. This interplay, creation versus constraint, sculpts the prime's unique distribution. The triangles are the fountain, the squares the basin. Together, they define the flow of primes. Not every number is prime, because the constraints filter the generative force. This dynamic, called boundary bulk, is the signature of the system. The primes are survivors of this cosmic tug-of-war, shaped by both expansion and limitation. The 14 faces encode the balance between possibility and restriction. Primes, then, are the result of this elegant geometric filtering. Boundary bulk dynamics are the engine of Grant's theory. The bulk, the 8 triangles, represents creative potential, while the boundary, the 6 squares, imposes limits. Primes exist at the interface, shaped by both forces. Like a sculptor chiseling marble, the creative force is shaped by constraint to reveal the final form. Early on, the generative force is strong, so primes are frequent. As numbers grow, constraints multiply, and primes become rarer. This explains why primes thin out along the number line. The boundary bulk dynamic gives a physical intuition for the prime number theorem's predictions. It's a geometric tension, creation versus limitation, encoded in the cuboctahedron. The distribution of primes is the mathematical echo of this cosmic balance. Geometry, not randomness, may be the true architect of the primes. A theory must make testable predictions. In mathematics, especially in the mysterious world of prime numbers, this is the gold standard. If a new idea can't be checked against reality, it remains just that, an idea, not a theory. The true test is whether it can predict something we can actually measure, and do so with precision. Grant's theory rises to this challenge with the iHarmonic prime counting function, a bold new approach that claims to do what no other function has managed before. Built from the unique geometry of the cuboctahedron, the iHarmonic function doesn't just estimate the number of primes up to a given number. It claims to count them exactly, with no margin for error, even at astronomical scales. Traditional prime counting functions, like Riemann's, always have a small error. No matter how refined, their predictions only ever approach the true count, never matching it perfectly. The iHarmonic function, however, matches the true prime count up to numbers as large as 10 to 30, a feat that has stunned mathematicians and computer scientists alike. This level of agreement is unprecedented. Its components are derived from the cuboctahedron's 14 faces and the interplay of creation and constraint. This geometric foundation is not just a visual metaphor, but the actual engine behind the function's accuracy. The I refers to the imaginary unit. linking back to the complex plane, while harmonic reflects the wave-like nature of prime distribution. Together, they hint at a deep connection between geometry, complex numbers, and the hidden rhythms of the primes. The function models primes as peaks in a geometric waveform, suggesting that primes are not scattered randomly, but follow a subtle repeating pattern shaped by geometry. Its astonishing accuracy provides strong empirical support for Grant's geometric theory. The data doesn't just fit, it aligns so closely that it's hard to believe it's coincidence. If the geometry were wrong, such precision would be impossible. The slightest error in the underlying structure would show up as a mismatch, but here, the fit is nearly perfect. The iHarmonic function may be the first tool to fully decode the prime's hidden order, offering a glimpse into the deep structure that has eluded mathematicians for centuries. To visualize this, imagine the ocean as the creative bulk, a vast, restless expanse, full of potential and energy, always in motion, always generating new forms. The ocean's surface is never still, and beneath it, countless forces interact, shaping the waves that eventually reach the shore. The shoreline, then, is the boundary, where the infinite possibilities of the ocean are met with the firm, unyielding edge of the land. It's a meeting point, a place where something new is defined. Each time a wave crashes, it brings with it energy and matter, leaving behind shells at the high tide mark. This is the interface of energy and constraint, where the ocean's creativity is shaped by the limits of the shore. Primes are like these shells, not scattered randomly across the sand, but appearing in a pattern that hints at a deeper order. They're deposited along a specific line, as if following an invisible rule set by the meeting of ocean and land. The Riemann hypothesis in this view suggests that all the shells, the primes, are found on this line, known as the critical line. Grant's approach offers a reason for this. It's not coincidence, but a consequence of the underlying structure. The line is the inevitable result of the ocean meeting the shore, a natural outcome of two forces interacting. The cuboctahedron is the law governing the wave's behavior, shaping how and where the energy is released and shells are left behind. The iHarmonic function acts like a map, predicting exactly where the shells will be found, revealing a hidden order beneath the surface chaos. This analogy shifts our perspective, from simply observing patterns in the sand to understanding the dynamic process that creates them. We move from seeing static arrangements to appreciating the ongoing dance between creation and limitation, between ocean and shore. The critical line is a mathematical shoreline, a precise boundary shaped by the interplay of these forces. It's a place where the infinite creativity of mathematics is shaped and constrained, giving rise to the beautiful order we see in the primes. The mystery of the primes, then, becomes a story of geometry and structure, a testament to the deep connection between chaos and order, not a product of mere chance. A geometric proof of the Riemann hypothesis could revolutionize mathematics. It bridges number theory and geometry, suggesting the universe's deepest truths are written in shapes and symmetries. If Grant's theory holds, it could inspire new approaches to other unsolved problems. The idea that numbers and space are two sides of the same coin could unify mathematics in unexpected ways. Of course, the theory must withstand rigorous peer review and scrutiny. But even if it's not the final answer, it reignites our imagination and challenges us to see old problems anew. Mathematics is a living discipline, evolving with each bold idea. By daring to see the rhythm of the primes in geometry, we may be witnessing the dawn of a new era in mathematical thought.